What if I told you, time can slow down? Not as a metaphor. Not as a figure of speech. Literally, time itself moves slower depending on where you are and how fast you're moving. What if I told you gravity can bend light? That a beam of light traveling in a straight line gets pulled off course by a massive object sitting in space? What if I told you that right now, the chair you're sitting on, the floor beneath your feet, your own hands, are made of atoms that are almost entirely empty space? That the solid world you live in is mostly nothing? And somehow, people still say physics is boring. Somewhere between the chalkboards and the equations and the textbook diagrams, we lost the plot. Because the real story of physics isn't about memorizing formulas. It's about the hidden rules that make reality work. It's about the code running underneath everything you see, touch, and experience. Time isn't fixed. Space isn't empty. Gravity isn't what you think it is. And the universe is doing things right now, at this very second, that defy everything your gut tells you is true. Physics isn't boring. It's just usually taught in the most boring way possible. So where did it all go wrong? Here's what actually happens to most people. You're sitting in a classroom, probably around age 15 or 16, and someone hands you an equation. Force equals mass times acceleration. Velocity equals distance over time. And your immediate reaction is, okay, when am I ever going to use this? Nobody showed you the weird stuff first. Nobody pulled you in with the part where time slows down near a black hole, or the part where a particle can exist in two places at once, or the part where light behaves like a wave and a particle depending on whether you're looking at it. They just handed you the math and expected wonder to follow. That's like giving someone the sheet music to a symphony before they've ever heard music. You've lost them before you started. Physics got turned into a school subject when it's actually a reality-breaking story. The greatest mystery novel ever written, except the author is the universe itself, and every chapter makes less sense than the one before it, in the most fascinating way imaginable. Most people who think they hate physics have never actually been introduced to physics. They've been introduced to equations about physics. And that is a very different thing. So let's fix that right now. Let's forget the classroom version for a moment. No equations. No memorization. Just the version of physics that bends time, warps space, and breaks common sense. Starting with the thing you think you understand better than anything else. Time. You've been living with time your entire life. You wake up, the clock moves forward, things happen in order, you go to sleep. Time feels like the most obvious, most reliable thing in existence. It isn't. For most of human history, we assumed time was universal. That a second here is a second everywhere. That time flows at the same rate whether you're standing still or moving at incredible speed, whether you're standing on the surface of the Earth or floating deep in space far from any massive object. Then Albert Einstein showed up and quietly dismantled all of that. What Einstein realized, and this is one of those ideas that sounds impossible the first time you hear it, is that time is not fixed. Time is flexible. And how fast time moves for you depends on two things: how fast you're moving, and how strong the gravitational field around you is. The faster you move, the slower time passes for you relative to someone who is standing still. Let that sink in. If you got on a spaceship and traveled at a significant fraction of the speed of light, and then came back to Earth, less time would have passed for you than for the people you left behind. You would have aged less. Your clock would have ticked fewer times. Not because of some illusion or trick, but because time itself moved differently for you. This is called time dilation, and it is not science fiction. It has been measured. It has been confirmed. It is real. Here's a version of it you interact with every single day without realizing it. GPS satellites. The satellites that power the navigation on your phone are orbiting Earth at high speed and at high altitude, which means two relativistic effects are in place simultaneously. Their high speed causes their clocks to tick slightly slower, but the weaker gravity at altitude causes their clocks to tick slightly faster. Engineers have to account for both of these effects predicted by Einstein's theories, or the GPS system would drift by miles every single day. Your phone knows where you are partly because someone did the math on how time bends near massive objects and at high velocities. Einstein was right. And your navigation app is the proof. This isn't abstract. This is built into the technology in your pocket. And if time can bend, then reality is already stranger than most people ever imagined. But that's not even the weirdest part. Look at your hand. It looks solid. It feels solid. If you knock it against a table, it makes a sound. It has weight. It has texture. Every instinct you have tells you that it is a physical, continuous, dense thing. It isn't. Your hand, like everything else in the universe, is made of atoms. And atoms are almost entirely empty space. Here's the scale of it. The nucleus of an atom, the dense central part, is roughly 100,000 times smaller than the atom itself. If you scaled an atom up to the size of a football stadium, the nucleus would be smaller than a marble sitting at the center of the field. The electrons that orbit that nucleus? Somewhere out in the stands. And everything in between? Nothing. The vast majority of every atom is empty. That means the table you're sitting at, solid, hard, unyielding, is made of structures that are almost entirely empty space. Your body is made of structures that are almost entirely empty space. The entire physical world you move through every day is mostly nothing. So why does it feel solid? Because of electromagnetic forces. The electrons in the atoms of your hand and the electrons in the atoms of the table repel each other with tremendous force. What you interpret as the sensation of touching something solid is actually your electrons and the object's electrons pushing back against each other. You never actually make contact in the way you assume. You have never really touched anything in the way you think you have. That's not a metaphor. That's physics. The solidity of the world is a kind of organized electromagnetic conversation happening at scales too small to see, creating an illusion of hardness and density that your brain interprets as reality. So matter is weird. Time is weird. And now it gets even stranger. Let's talk about gravity. You already have a mental model of gravity. Things fall down. Objects with mass attract each other. Isaac Newton described it in the 1600s. And his description was so accurate that we used it to calculate the orbits of planets and launch spacecraft for over 200 years. Newton's model of gravity was brilliant. But Einstein's was deeper. Here's what Newton's model essentially said. Massive objects pull on each other across empty space through an invisible force. And for a long time, that was good enough. It made accurate predictions. It worked. But Einstein asked a different question. Not just how does gravity work, but what actually is it? And what he found changed everything. Einstein's insight was that gravity is not a force being transmitted through empty space. Gravity is a consequence of geometry. Massive objects, stars, planets, black holes, don't just sit in space. They bend space itself. They curve the fabric of space-time around them, and other objects moving nearby simply follow those curves. There's a common analogy that helps here, even if it's imperfect. Imagine a stretched rubber sheet, like a trampoline. Now place a heavy bowling ball in the center. The sheet curves around the ball. If you roll a marble near it, the marble curves toward the bowling ball, not because the bowling ball is pulling it with an invisible rope, but because the marble is following the curved surface. That's essentially what's happening in space. Except instead of a two-dimensional sheet, it's four-dimensional spacetime. And the curves aren't visible. They're geometric distortions in the structure of reality itself. The Earth doesn't orbit the Sun because the Sun is yanking on it. The Earth orbits the Sun because the Sun's mass has curved spacetime in such a way that the Earth's path through it naturally curves in a closed loop around it. This also explains something remarkable. Light has no mass. Under Newton's model, gravity should have no effect on it. But under Einstein's model, because gravity is geometry, and light travels through the same spacetime that gets curved by massive objects, light bends too. We've observed this. Stars near the edge of the Sun appear slightly shifted during solar eclipses because their light is being bent as it passes close to the Sun. We predicted it. We measured it. The bending was exactly what Einstein's equations said it would be. Gravity is geometry. And once you realize the universe can bend space and slow time, black holes stop sounding like science fiction. Let's talk about black holes. First, forget everything movies told you about them. They're not giant cosmic vacuum cleaners, sucking up everything in the galaxy. They don't roam through space hunting for victims. If the Sun was suddenly replaced by a black hole of the same mass, the Earth's orbit wouldn't change. We'd have a lot of other problems, but the gravitational pull would be identical. What a black hole actually is a region of space where gravity has become so extreme that the escape velocity exceeds the speed of light. Escape velocity is the speed something needs to reach in order to break free from a gravitational field. Earth's escape velocity is about 11 kilometers per second. Fast, but achievable. We launch rockets out of Earth's gravity all the time. For a black hole, the escape velocity at and below the event horizon, the boundary of no return, exceeds the speed of light. And nothing in the universe moves faster than light. So nothing that crosses that boundary can ever come back out. Not matter. Not signals. Not light itself. This is where the physics becomes genuinely cinematic. Near a black hole, the time dilation effects we talked about earlier become extreme. Time slows dramatically in intense gravitational fields. Near the event horizon of a massive black hole, time would slow to a crawl relative to an observer far away. If you imagine someone watching you fall toward a black hole from a safe distance, they would see something strange. They would see your clock tick slower and slower as you approached the event horizon. From their perspective, you would appear to freeze at the boundary and slowly fade, stretched by the distortion of space-time and redshifted as the light from you became increasingly strained. From your perspective, if you were falling into a large enough black hole, you might cross the event horizon without noticing anything unusual. The horror comes later. Black holes also warp light. They can act as gravitational lenses, bending the light of objects behind them into rings and arcs. We have photographed this effect. We have imaged the shadow of a black hole at the center of the galaxy Messier 87, a region of darkness surrounded by glowing material being heated as it spirals in. We have a picture of a black hole. A real one. Physics didn't just predict it. We went and looked. This is where general relativity, Einstein's theory of gravity, gets stress-tested to its absolute limit. And so far, every time we've tested it, it has held. But the wildest part of physics is not just that the universe is strange. It's that we can actually understand parts of that strangeness. Here's the thing that should genuinely blow your mind. We are humans. We evolved on a small planet orbiting an unremarkable star in one of billions of galaxies. Our brains developed to do one thing: to survive. To find food, avoid predators, navigate social groups. And yet, somehow, using those same brains, we figured out that time bends. We figured out that matter is mostly empty space. We figured out that the universe began in a state of extreme density and has been expanding ever since. That gravity is the curvature of space-time. That particles have quantum properties that don't behave classically. That the same light can interfere with itself like a wave while also striking a detector like a particle. We didn't just discover these things by accident. We reasoned our way to them. We designed experiments. We built instruments sensitive enough to detect gravitational waves, ripples in spacetime caused by black holes colliding, that stretch and compress space by a fraction of the diameter of a proton over the distance of 4 kilometers. We built a detector sensitive enough to feel the universe shake. Physics is not about memorizing formulas. Formulas are just the compressed language of much bigger ideas. Physics is humanity refusing to accept that reality is a black box. It's the ongoing, never-finished project of asking the universe how it actually works, and being rigorous enough, creative enough, and honest enough to accept the answers even when they're deeply strange. From Newton watching things fall to Einstein bending spacetime to quantum mechanics suggesting reality only becomes definite when you observe it, physics is the story of how we've cracked reality open, piece by piece. It is one of the most audacious things our species has ever attempted. Physics is the art of asking reality questions it cannot lie about. And we are still asking. So let's recap where we've been. Time is not fixed. It bends based on speed and gravity, and we've measured it, built it into our technology, and confirmed it over and over again. Matter is not solid. The world you move through every day is mostly empty space held together by electromagnetic forces, and you have never touched anything in the way you instinctively believe you have. Gravity is not just a force. It is a curvature in the fabric of spacetime, and massive objects don't pull, they bend geometry itself. Black holes are not science fiction. They are real, We have photographed one, and they represent the most extreme environments in the known universe, places where everything we've discussed today becomes maximally strange. Your everyday reality, the ground beneath you, the sky above you, the clock on the wall, is far stranger than it appears. So no. Physics is not boring. Physics is terrifying, and beautiful, and absurdly fascinating. The only boring part was the way it was introduced to you. If this changed how you see physics, subscribe for more. Because this was just the beginning. Reality gets even weirder from here.